like to invite Professor Ashwin Ittoo, Enabling and Helping Industry with AI Implementation, University of Leeds, with the topic Leveraging AI Research for Actionable Insights in Decision Making. Let's welcome Ashwin with applause.
Thank you very much for your introduction. It's a pleasure to be with you today at Luch. Unfortunately, I won't talk to you about sports cars. I love cars, but my topic will be a bit different than cars. I will talk to you about research on AI and how we exploit this research for industrial use case. I will also use my time to speak about responsible AI to pave the way for our exciting panel that is coming up soon. This is me, my name is Ashwin Ittoo. I work in Liège, in Japan and in India. And on the right, you can see a few of the companies with whom I collaborate. And I will illustrate some of the use cases we develop with them, the risks and challenges that are also associated with these AI systems. So I will focus my talk on three main pillars. Firstly, AI research and use cases. Then the sexy topic of LLMs and their applications, as well as their risk. And finally, responsible AI, specifically on the carbon footprint of these systems and the issue of bias and stereotyping. So first I will start with leveraging insights from AI. It's a research project which was done with a consultancy company known as KPMG, which probably you have heard of. And this research, in this work, KPMG wanted to learn about weak signals. Now you might be wondering what are weak signals and why would KPMG be interested to learn about weak signals? In fact, a weak signal is an event or a phenomenon that is being discussed in media, which is in its infancy, but which has huge business and investment potential. It is not yet mainstream, but in the short or medium term future, it is supposed to have important business ramification. And detecting those weak signals enable the company, of course, to anticipate risk and to detect hidden opportunities. In that particular case, the customer that we were working for wanted to learn about weak signals for HR analytics, such that it could then use these weak signals to update and enhance its employee training procedure, but also attract new talents or align and update its recruitment policies. So to do so, we develop an unsupervised learning method. That is, we don't need data which is annotated, because we don't know what are weak signals. We can't annotate our data beforehand. If you want to learn more about it, we can discuss more in the break or later. What we did then, we collected around 500,000 job advertisements from Indeed.com, from Monster, and so on, in unstructured textual format. We applied our technique to these job advertisements to extract those weak signals. Our technique, from such unstructured text, discovered three main themes about the job market. So the customer here had a question, how was the job market evolving? What are skills that are in demand? What are skills that are declining? This is why we use such text and applied our algorithm to extract weak signals from that. And our algorithm automatically extracted three main themes, which you can see here: job titles, languages, and skills. Then from these three main themes, it also generated a hierarchy of sub-themes or more specialized topics. For instance, in job titles, you have different kinds of job titles. In skills, you have different types of skills. So this hierarchy was automatically created without any human supervision. Now, where are the weak signals? All the themes and or topics in yellow like data engineer at that time, Rust, low-code development were topics that were only being weakly mentioned in those job advertisements, but which had huge potential. On the other hand, you could see that some of those topics like Java, PHP, and so on were on the decline. So then that company, it was a company in the telecommunication sector, once it had knowledge of all these information, it could use it actually as actionable insight. Why? Because these were directly applicable to their HR recruitment policy, to their employee training program, and also to their branding. Then they could say that they are avant-garde and modern organizations working with the latest technology to give customers the best service possible. So from research, unstructured text, we get those kind of actionable insights. Now, those weak signals, they are not only used in business, they are also used, for instance, by the national security or the defense sector. In this use case that we did for the defense, the aim was to find out what is being said by countries or about countries in tweets. And we extracted such a graph from tweets in which you can see countries and the topics that are being discussed between those countries. Using such a graph, the intelligence analyst can then detect latent topics, so new topics that have just emerged, and maybe connections between certain countries that are not explicit. Obviously, there are many other applications of weak signals detection in finance, in investments, and so on. The next use case that I'm going to illustrate, the famous topic of large language models. Specifically, I will show you how we use large language models to automate the process of reporting. So, as you know, the European Commission requires that companies report information to them. It's called regulatory reporting obligations. Companies need to report some information to some entities by some deadline. So who reports something to another institution by that deadline? But those reporting obligations, they are in completely unstructured text, which means that lawyers or compliance officers have to read such text and decide what they should report. One example of a reporting obligation is what you see here. I will give you a bit of explanation soon on what is this reporting obligation later. But the aim was to start from this unstructured text. From that text, create an ontology in OWL, O-W-L. Why did they want to have a structured formal OWL representation for business process automation? With such a formal representation, you could automate the process of compliance checking, but also of enforcement, that is knowing who has not reported what by which deadline. Now, before you can build such an ontology, the first step was to extract key entities, key elements that define a reporting obligation. So together with lawyers and analysts from the Commission, we define what were the key entities of the reporting obligation. You can take the first example here, very briefly. In all reporting obligation, you have an addressor who reports. Here the Commission, to whom, European Parliament and the Council, what should be reported, a report on the issue of the reprocessing of medical devices and so on, and by which date. So we had to extract those parts of the sentence, those entities, to populate our ontology. The first approach that we adopted was a pure NLP approach, and again, we have no data that has been annotated. we had to have to recourse to various tricks, and we use an approach known as syntactic parsing to extract the syntactic dependencies across all sentences of such text that I showed you earlier. Once we had those syntactic trees or graphs, we had to parse them to detect the key elements. For instance, here we have the to, report to whom, to the parliament and to the council. So we had to detect that this entity was identified by a rule which has a propositional object, a conjunction, and a conjunction. It was extremely, as you can imagine, tedious and painful to write such parsing code because sentences were completely different from each other, and each time had to adjust how we traversed those graphs. It was simply impossible to continue that way. This is when we decided to use Llama. Why did we use Llama? Well, for a number of reasons, but also because it was partially open source, unlike GPT, which is completely closed source and proprietary. So we adopted a technique known as few-shot learning, in which we give Llama an example of a sentence, of a reporting obligation. We gave it an instruction, what it should do, and gave it an example. That's all, which is much more simpler than having to use syntactic parsing. And of course, it worked fine. It could automatically extract those entities from the reporting obligation. But then, even though LLMs and Llama seem to be very promising, was it the final or the holy grail that we were looking for? Actually, no, because there were a number of points that deserved further attention. What were those points? First, few-shot prompting. As I said, you use a few examples to show it to your LLM that it can learn. But the choice of the exemplars is crucial because they will determine the coverage of your output, of your response generation. Second important point, the issue of transparency. We could not explain how the LLM reached a particular result. Specifically, in cases where it gave the wrong answer, we could not debug as we would have done in normal code. The issue of cost. Well, you might argue that Llama is open source and so on. Yes, that's true, but you need to have manpower and you need to have infrastructure to run such a large language model. Finally, the issue of hallucination. For our daily use, if GPT or any LLM hallucinates, that's fine, it's funny. But if you deal with reporting obligations and the LLM gives you false information, then you might end up into trouble if you believe what output the LLM is telling you. So you cannot simply trust the result produced by an LLM. As you can see here, it is telling us that you have to report something to the computerized database and to the registers. But the text doesn't mention anything like that. It is inventing or giving you misleading facts. And for a company, this can spell trouble and huge penalties can follow. So LLM, yes, they work fine, but can they be trusted? Probably to some extent. One solution, of course, is to use RAG. I guess you know what is RAG. In any case, I saw tomorrow you have a session on RAG. RAG means Retrieval Augmented Graph, in which you use your internal database, your internal data as context to the LLM to guide it to produce the right answer. But you will learn more about it tomorrow. And RAG has many advantages compared to fine-tuning because you don't need to train your LLM. You just vectorize your existing data, take it as context, and feed it to your LLM to generate its answers. So we have seen two use cases, how AI research is being used by organizations and by companies for various purposes, for HR analytics and by the Commission for reporting obligations. Now, the responsible part of AI. I will focus on the carbon footprint. So, you know that GPT-3, ChatGPT that you use was based on GPT-3. It's a very powerful model, very large model, approximately this number of parameters. But the carbon footprint was estimated to be 552 metric tons of CO2. And this value here includes the cost of embodied carbon, that is the cost needed to manufacture the hardware, and the cost of electricity used during the training procedure. Then GPT-4, which came afterwards, a much larger model, obviously will have a higher carbon footprint, even though estimates are not known. Now, to give you a better idea to compare what these figures stand for, if you take an image generation model and you ask it to generate 1,000 images, then the energy consumed will be equivalent to 1,600 watt-hours, which is equivalent to charging a smartphone 70 times. And all these figures, actually, they come from this nice research, which says, hey, now, LLMs are getting more and more popular, more and more ubiquitous. We are all using them. But we have to start to think about their carbon footprint, because this is not negligible. Just like light bulbs, which we use on a daily basis, LLMs are also going to be used on a daily basis. So what they say in this publication, if light bulbs have energy ratings, why don't we give energy ratings to LLMs as well? And one more article which is quite interesting, it tells you, well, Gen AI environmental costs are soaring, and no one is currently talking about that. So in my opinion, this would be a big topic, a weak signal for the coming years. And what we are doing in that respect, at our side, we can't do much more. We are only a university, we are not Amazon or Google or Meta. So what we are doing, we are taking existing models like Llama in architecture, Llama in code here. We are trying to reduce the size of existing LLMs without compromising on their performance. Just to give you a brief idea, and of course we can discuss more later, we focus on the Llama attention layer, and we try to reduce the size of the matrix inside it in various ways by the classical singular value decomposition, if you still recall your statistics, or by an autoencoder to try to compress the size of the matrix at the attention layer. But that's quite technical work with the aim of trying to reduce the size of Llama. And why Llama? Because it's open source, you can easily get the code and start to work with that. So LLM and carbon footprint is one big topic that is coming up in the future, at least I believe. One more topic that is already an issue is the effect that AI systems in general tend to amplify or over-amplify stereotypes, and sometimes wrongly make decisions which can lead to bias and discrimination. I have chosen 2 or 3 examples here. In the first one, this is a well-known case whereby a generative model was asked to generate images of typical CEOs. And it was more or less men with glasses of a certain ethnic group with a shirt and a tie. And then this is also a case which is quite dated now, 2016. Someone was asked to upload a photo for his passport or driving license, but the application refused the photo on some facial characteristics, which was quite natural in that case. That person couldn't do anything about that. Because the AI system thought that he was closing his eyes, but it was not true. His eyes were naturally like that. Then you have heard about the case of Mr. Eric Loomis in the US, which I have not mentioned here. He was arrested for a drive-by shooting. He was brought to the court, and then they used an algorithm known as COMPAS, C-O-M-P-A-S, to give him a recidivism risk score, how likely he is to commit a crime again. And that algorithm gave him a very high score of committing a crime, and he was not released on parole. And his lawyer was quite smart. He said, let me inspect the data on which COMPAS was trained. And he saw that this training data had one variable for the race and was dominated by one single ethnic group in the US, which was tagged as high scores of committing a crime again. The race, since Mr. Loomis belonged to that majority race, he was automatically predicted as having a high risk of committing a crime. It's a very well-known documented case, or the case of Eric Loomis against the Wisconsin state in the USA from 2016. All that to tell you, well, we had the issue of transparency that I explained with LLMs before. You take this photo and a deep learning system would predict it correctly as a panda. You add some random noise to it, and you tell the same algorithm what is that image. To us, visually, there is no change, but to the underlying pixels, it gave the algorithm completely gave the wrong answer and said that this panda is apparently a gibbon, which is completely fake, and which links back to what my colleague said, I think, before the lunch break. Computer vision systems in car tend to fail simply because of that. The slightest change in a traffic sign will cause it to completely go haywire, even though to the human eyes, the image of the traffic sign is still very much perceptible. Thank you very much. So just to conclude, as you have seen, I work on technology a lot, use cases, KPMG, commission, and so on. But at the back of my mind, and I think at the back of all of our minds, the responsible use of AI is extremely important. And the next session, the panel in place, will shed more light on this issue. Thank you very much, and enjoy yourselves.